In the last two sections of Chapter 5, we looked at the principle of mathematical induction. We're going to look at another flavor of mathematical induction in this section. Remember, the principle of mathematical induction said that if we have a sequence with a group of integers and some property relating to each one of those integers, which we might define, say, with an explicit formula, we will soon see there's other ways of defining it. We're saying if this property is true for the very first one, and if you can pick some random location along the way, k, that's bigger than the first one, we're saying if we assume it's true for the kth one, and we can prove that it's true for the k plus 1th one, which is the next one, then we're going to say we're going to assume it's true for all of them. In this section, we're going to look at another flavor of induction called strong induction. It's very similar to the regular induction, or the plain vanilla induction that we've been doing, and it's mathematically equivalent to it, but it works just a little bit differently. What it says is if we, again, have a sequence starting at A, and we have some property here, well, if we pick some second location, B, and we can show that this property is true for A plus 1, A plus 2, all the way through B. In other words, if we can prove that it's true for a group of these things at the beginning, this forms our basis step. So what we have here is multiple basis steps. We're then going to say if there's an integer k greater than or equal to that second location, if we can say if p of I is true for all of the ones from A through k, then p of k is going to be true. It's a little different flavor of the inductive step. We compared this in a classic way to being able to knock down a set of dominoes. When we did regular induction, we did two things. We first of all showed that we could knock this over for the very first one. We could knock over the first one, and then we picked some domino in the collection, and we said if we can show, that it's true for p of k, that we could then knock over p of k plus 1. In other words, if we can knock over the kth one, we can knock over the k plus 1 one. Strong induction is just a little bit different than this. What it says is we're going to pick some starting location. Let's just call it the first one, but it could be any place. It could be P sub A. And some second location, P sub B. If we can show that this property is true for all of the ones in this first group, and if we can show that when we assume that it's true for p sub k and all of the ones before it. In other words, we're looking at p sub I, or p of I, when I is something between b and k. So we're really saying it's all the ones down to here. Okay? And since we've already proven that it's true for all the ones in between, we know it's true for all the way up to here. If we assume that, then we're going to say that the next one, p of k plus 1, is also true. So this is a little bit different than regular induction because we have several basis steps. And instead of only assuming that one thing is true, we're going to have to assume that this property is true for everything back to the last of the basis steps. then it'll be true. If we can then show that it's true for the next one, we will assume that it's true for all of them. Again, this is a principle or axiom that we are working with. It's something we are going to assume is going to work. It is mathematically equivalent to the regular induction idea. This one is very useful for us in computer science because we often have algorithms or routines or subroutines where you have more than one seed, more than one place where it starts. We'll be looking at some of them. And if we want to see that this works for all of the cases, sometimes figuring out how one case works means we have to look at more than one case before it. This is what happens in recursion, which is something we're going to be examining in one of the next sections. So it's very important to be able to use this in doing proofs that involve recursion. Finally, there is a third statement that is equivalent to both regular induction and strong induction, but it really doesn't look like the other ones. It's called the well-ordering principle for integers. And it says if you have a set of integers and it contains one or more integers, all of which are greater than some fixed integer, and you say all the integers are greater than 50, or all the integers are greater than 20. Well, then this says this would have to have a least element. This statement is very different from our regular induction and our strong induction, but it is equivalent to them. And there's a discussion in your text about how it's equivalent. While this is a mathematically important statement, I think you're going to find that strong induction is the thing you're going to use in doing some computer science problems dealing with algorithms. So we're going to be concentrating on how to be able to do proofs using strong induction.